So once again, Vincent Lafage from IGC Lab, directly from the Jurassic era, on bringing it to the doors of the stars. So we are back to the Fortran, as you have probably noticed from yesterday. We want to go to GPU. So we'll see today 3 ways to do so, among others. So I will start with a short overall presentation of the topic, and most will be hands-on. So as you certainly noticed, the GPU use a very large parallelism, so we want threads, lots of threads. And the 3 main ways to get your Fortran code to GPU. Okay, so older style was OpenCL, and OpenCL is C. So you would need to bind it with a C language, and it's very heavy. The nice point of OpenCL is that it works everywhere inside, even out of NVIDIA. And the modern replacement would be Vulkan, that also has the same characteristics, but it's really too heavy for what we want to do. We want to start from our good old Fortran and make it use GPU. So the first high-level language on the market that allowed this was from NVIDIA, and it was CUDA Fortran. It's exactly like CUDA for C++, but for Fortran. So you get extra attribute that we'll shortly see. I won't advocate this, and I won't use corresponding code for Gray Scott. We'll shortly see that we can use the CUDA libraries, in particular QBLAS and QRound, in this context. Okay, the negative point is, of course, it works only on NVIDIA. What we'll, in fact, start with is directives, and in particular, OpenACC. So they are also mostly NVIDIA-oriented. And we'll see that expressing the parallelism is not the hard point. And the hard point is to get explicit memory handling. There is also OpenMP, which is not only for multi-thread and vectorization, but allows you, starting with version 4.5, to offload some of your kernel to a GPU, to an accelerator device. So we'll see this. And we'll conclude with what is the best way, but in which we have no control over the result, using only modern Fortran with do concurrent. And it is the so-called STD-PAR, standard parallelism of NVIDIA. In fact, NVIDIA tells you there's nothing to do. Not really. So the first thing we discover when trying to use GPU is we need the good kernel module with the right kernel and also with the right GPU compute capability. So, and as we will see, also with the right compiler. So you have to align a lot of parameters, and it's a lot of system installation that you have to do. So your, in some sense, hello world starts before you start programming, when you can get the NVIDIA SMI of your computer producing you this kind of result. Starting there, you know that your GPU is on and your kernel can access it. So this was an early attempt to use Vulkan in Fortran. It needed to define a lot of parameters before even trying to program something. So I did not continue along this way. It provides you access to all the detail you want. And the next step would be some CUDA Fortran example. So here you have the typical compilation line. And you have specific attributes for CUDA Fortran, such as the global attribute for the subroutine. On top of which, you have these variables, such as block dim, block IDX, that CUDA user know, as well as this kind of attribute device that tells you that these variables, this array, are defined on the GPU. So not only you need this specific CUF for CUDA Fortran extension, not only you need the NVFORTRAN compiler, but you also have to modify your Fortran to design where is stored your variables. And then you have the kernel call with this specific bracket syntax. So it is called Fortran, as in CUDA Fortran, but it requires a lot of change to the code. So it means that for some cases, we need to maintain the CPU code and the GPU code on different sources. So we would like to avoid this. So you will find at this GitLab, which is the same that I shown last time, the example files as well as the solution. So please give it a try. Who has a GPU? Okay. So we have images. I will send the images. So as for the last time, we have a make file that was mostly for the CPU part, with a lot of targets, and the code has not changed much considering the word cloud. So we still have all the variables defined here, but we'll read them from the NML namelist file defined also last time. So the init field has been changed to take the same definition of the drop of V as you will see in the code. Okay, the parameters are extended to the sizes. So as last time, I couldn't show you the OpenMP multi-thread version. I will correct this right now, and then later we'll move from thread to GPU, so that you can see the directive at work on how we get some performance out of the CPU first, and then how it helps us to move to the GPU. Okay, so I took the source from Git, and then can you read?
Yeah.
Okay. So last time, we had this, a module with the setting, then among the possible stencils, we chose the ISO one. So here we put some HDF5 file into play with the dataset name of matrix. And in the introduction, we read the values inside the namelist file, and we write them to the output in order to check that everything is working. Okay. Then there is some black magic with the HDF5, but you can check in this other file all the definition. It's very verbose, but you can find example to call to open the various level of your HDF5, starting with opening the interface to HDF5, creating a file, creating a data space, creating a data set inside the data space, chunking the data set, deflating, compressing if the Boolean variable is set, and creating data set with the properties as well as memory for the data space. And then there is this ability to write only a slice of it. Okay, so black magic. So the initial version was very old-style Fortran. We loop over the column and the line, because Fortran is oriented this way for array, and then we sum over all the cases of the stencil. So this is only setting the initial condition, putting an absence of U in the middle on the drop of V at the right, at the same place, and setting the boundary conditions for U and V. Then we have this old style routine that we may have to compare when we want to write out without using HDF5. On the main program here, allocates memory after the initialization phase. And we had this wrongly placed OpenMP directive. Okay, why is it wrong? Okay, so this main loop here is the loop over time. And this one is a real iteration. It's not any implication, multiple. All these, the step of this loop depend on the previous one. So we cannot parallelize it. Okay. Beside this detail, as long as you don't set OpenMP, this program should not be a problem. On the main loop is quite short. We compute the formula with these rather compact lines where we have separated the computation of the Laplacian for U and the Laplacian for V in separate array before the main loop. So we have defined maybe a bit more, too much memory, twice as much, not so good. And then we put back the result of U1 in U0, and we start again. We write out the solution, and we close. So this was the initial status of the code. And it needed some rewrite before being usable for what we want. So first, OpenMP. Okay. So maybe we'll start with a short number of steps. But in fact, it will be overwritten, so it's not a problem. We'll use this trick, which is to write to a device in memory instead of writing on the disk. In this way, we'll be able to get some speed up. But not the one we are interested in. In order not to compute the Laplacian for every case of every places on the field, we will turn to this computation here, where we compute the Laplacian with the sum of the stencil times some excerpt of the field. So we only compute it in one place, and then we use it in the same formula, but as a scalar rather than as an array. So we explicitly write all the j and I. We run over all of them. So this subroutine will compute one step of evolution. And then we update the result by writing if the logical value is right. One slice in the HDF5 file that is open. And so we find the main program that starts with the initialization of the settings of the field. We get the evolve subroutine to run over all the iterations for the number of steps. And at the end of each iteration, it decides whether to update if the number of iterations is a multiple of the intersave count. Okay. And we close the file. And we display the number of microseconds spent. So we check once more the settings. Okay, 320 steps. Will not wait in vain. So let us go to all the details of the compilation. So we first get things working on the CPU. So we ask for the debug information because we want to see in which line we have problem. We set all the warnings. We recall the compiler that if anybody forgets an implicit known, it should be punished. We ask for the how fast. We want to get the best of the native architecture. If there is some vectorization, it will be here. And we also will use any OpenMP that will be in the file. But as we have just seen, looking for OMP, there are none. So this code is pre-OpenMP. It's purely serial. Okay. And then we ask the compiler to unroll loop, to vectorize, and to display information about the optimization. We add the link to the HDF5 modules. So don't forget, in Fortran, a module file is what takes the role of a header file in C or C++. The problem, the good part is you don't have to maintain this header file on top of your source file. The bad thing is that every compiler is generating a different format of mod file. And as we'll all be moving to GFortran 15, it will not be compatible with GFortran B415. And of course, not compatible with NVFORTRAN or Intel Fortran. Okay, so we take the file compressed hyperslabs. The one I've just shown you, which is in the solution, which is pre-OpenMP, no parallelization. We link it and we execute it. Okay, so we should do this, but before, we'll do the same thing without optimization. So without optimization, no vectorization, no OpenMP, only this, and when we execute it in the end, we have no thread. Okay? So it reads the value. We know it is going for 320 steps. Okay, and so, okay, it's already finished, hopefully. So it took 21 seconds for 300 steps. It's not very good. So in turn, we'll add some optimization, starting with OFAST. Yes. So here the optimization are displayed. You see there have been a lot of them, and we have been from 21 seconds to 1.6, 1.7 seconds. So more than 15 of speed up. And we have not been asking for vectorization, but OFAST is setting some of them directly. So do we win much by setting all the vectorization options? Not quite. So it was vectorizing without waiting for our permission. So given this, let me show you what should have been the last time result. What happens when we use directive and we move from pre-OpenMP to OpenMP? Okay, sorry. Okay, so it starts in the very much the same way. Then in the evolve subroutine, we have this notation. So this is not an OpenMP directive. This is an OpenMP directive. You see the comment, which is the exclamation mark, the dollar, which combines with the comment to tell the compiler, when you ask for OpenMP compilation, take this into account. But this code on this side, the OpenMP version, is in fact good to be compiled for a sequential version. So inside the iteration over all the steps, so when before going further, when you have this notation, it means these lines will be compiled only when you are compiling OpenMP. And in this case, it will use OpenMP lib module, which allows you to have some functions, such as this one, OpenMP getThreadNum, that will tell you the number of the thread that is running this code. And here you see also that this standard if will only start when you have the OpenMP compilation option. Okay, so we define what is inside the time iteration loop here as one parallel region. So it starts here and it ends at the bottom here. It means that from this point, you have as many threads as you will define. So you can define it in the program. You can define it with an environment variable, as we will practice regularly. And these threads will live from here to there. And of course, it's up to the OpenMP implementation to keep a thread, a pool of threads, so that you don't have to recreate them at the end. You only pick them back when you enter the parallel region. And now we define the easy part, which is saying that the following loop has to be separated among threads. So all these 1078 loops will be separated among threads. The next level here is that we ask for SIMD of the inner loop. We will try to vectorize whatever occurs inside this inner loop. So now for the less obvious aspect. Here we have to declare that some variable will be shared among threads. So it's easy to read them from a single value, but it means that if you have a write variable inside this shared region, you can do stupid things and overwrite things that should not. So you have to think about not overwriting with one thread what you are writing with another. So our two fields, U0, V0 on the next step copy, U1, V1, all these fields are shared among the threads. N step is a constant, iteration is a constant among the threads, and I and J are the loop indices, so they are shared. Then we see also that we have this private value that are not the same in every thread. You get a copy of the, you get an independent space for lab Q and lab V in each thread. So we know that we will not overwrite the, yes?
Can you explain a little bit about the SIMD alignment and what is the safe len? I didn't know that OpenMP is also responsible for vectorization.
So this tells the compiler that U0, V0, U1, V1 are aligned in memory. So it has to take the proper steps for this. On those lengths across which you can safely vectorize will be as much as 64 bytes. Mm-hmm. But, well, of course, it would be really in the best case with AVX 512.
This is hardware dependent, or
is it?
This is hardware dependent.
Yes, yeah. Absolutely. So, welcome to vectorization. We introduce a lot of dependencies. Okay, so here we have a very classical step, which is checking that the so-called master thread is running, and only the master thread will display something. So, okay, except for the final message, we have the same thing. So now we will compile with a lot of vectorization options and a lot of optimization options, everything that we want, including the OpenMP setting that will trigger all these directives. So we should always start when multi-threading some Fortran by testing that it works for one thread. So we should expect the same result as sequential, more or less. Here we go. And same number of microseconds. Okay, that's good. So now we can check that with two threads, we expect a speed up. Not so much. So maybe it is time to play the game with a bit more work to do. Okay, so you can see that the whole clock time is only 10 seconds, but the user time is twice as much because the two threads have been working. Okay, does it scale? Let's move to 4 thread. In fact, it scales well. We went from 10 seconds to 5.6, not too bad. Maybe it's also time to give some much work to, a bit more work to do. Okay, so twice as much, and we went from 5.6 to 11. It scales well. And this machine has 8 cores, so we should expect the same speed up of 2 once more. And this is the case. So there is certainly some overhead because the total CPU time went from 45 seconds to 49, so almost 10% is spent. So we are now ready for the full scale image. So as you can see, all the cores have been working. And we have 32,000 images in almost 32,000 microseconds. One step by microsecond. So this is nice. And now that we know that the CPU can do this, we'll attempt to do the same kind of thing with the GPU. So you can take in solution the pre-OpenMP file, and instead of using OpenACC directive, we'll try to use instead of using OpenMP directive, we will use ACC directives. So while you look at the aspect of the ACC code, I try to reuse some extra vectorization options. Okay. So before this last multi-thread vectorization compilation, you can check for the various flag of your CPU using this /proc/CPU info. So it's a bit verbose because you have a lot of cores and you have the repetition of all the flags for each core. And you see that there are a lot of them. It's a bit difficult to know what it means. FPU, okay, there must be some FPU somewhere. And then you see that AVX 512 has a lot of declination. It appears in 1 or 2 dozen flags. That maybe don't exist on all AVX 512 CPU. So collecting all these specific flags you can tell your compiler that all of them are here. Will it help? Let's see. So we see that half the core are running. Of course, we don't send the hyperthread one. We don't want to lose time. And then we have 23 seconds instead of 31. So please be cautious with what exact kind of CPU you have. Telling AVX 512 is not enough. Go into the detail and the compiler will help you. Okay.
Sorry?
Yes?
Is it possible to copy your comments? Because it's a bit hard to try to run everything at the same time as you.
Sure.
Because it's quite long every time. So
should I share it with the Discord?
Yeah, thank you.
Okay. So, okay. For people starting with the OpenACC, now we'll have to use the NVFORTRAN compiler. But before leaving the wonderful world of CPUs, I will try to look at the other big compiler, the one from Intel. So for those of you who have the Intel compiler installed, this is the way to ask for it to be installed. We check ifx minus version. Okay, this is the recent one. Okay, so I share this for those interested. So here we see Intel compiler, debug option, optimization, all warning, implicit none by default, start OpenMP, SOX. Okay, we start with only the default AVX 512. And as I mentioned, each compiler needs a different module. So we go to a different set of include compiled explicitly for Intel. for the HDF5, then we use the HDF5 library designed for this case. And we'll start with this. So as we'll be looking into a different libraries than the default one, before the execution, we set also the library path to look for the Intel Fortran library. So as we see here, we have 50% of the core that are used, but in this way, we don't have the other core. So what went wrong? We are 10 times worse. Whoa, surprising. So I will provide the same detail of the vectorization. This is surprising. So, okay, 31 seconds, not better. Fortran made a nice work out of it. So, anybody has an ID for the OpenACC directives? As a reminder, we would use OpenMP in this way, defining a parallel region and detailing what loop are to be parallelized and looking for the variable that are shared and the ones that are private. So let's look first at some GPU examples. So you can find this GPU example as a GitHub gist. I share the URL. So we have a module with the common data. They also have 2 copies of one field of the same size. And they start with very basic initialization. So you have limit condition for the first and last column. And the first and last line are set to 0. So the ACC directive looks very much like the OpenMP directives here. We specify which data are copied from the CPU memory to the GPU. So you'll get a copy of A at the start of the parallel region. And you will create, which means create on the GPU, on the device, your copy anew. Then, as long as some error is greater than some fixed value and the iteration do not exceed some other value, we call the Jacobi relaxation step, call A. We compute the error, it's called error A, and we update A. And then we have the end of the parallel region on the GPU. So the results are written on Jacobi.dat file, and you find routines there, use common data. And this defines the parallel loop with a reduction. Well, in fact, this will have no effect because there is no max value, no error value computed with a max reduction. This is only this kernel that is split across loops, across the first layer of loop, and then the second layer of loop. And as you have already seen with other languages, this is common for GPU to split with 2 layers of loop. So here, update is a copy of anew into A, and this is done with the same structure of ACC loop. So if you can, if you should remind only one part, here we don't have the ACC end loop at the end, contrary to what appears in OpenMP. And here, in this parallel region, we have, in fact, a reduction of the variable error, which is the max across all threads in the parallel region. So we only keep, in this way, the max error across all the threads in the field. And in the end, we write it. Okay. So when we try to reproduce what we just learned. Okay, things change a bit. So on your left, you see the pre-OpenMP not parallelized program. On the right, what it becomes when you use OpenACC directives. Okay, so maybe let me compare it to the OpenMP version. So the first occurrence of this ACC region defines a data region, not a parallel region. So we prepare data in advance before declaring the ACC parallel regions. So in the main routine, we go from here to there with data U0 and V0 that are copied from the main, the CPU, and we create U1 and V1 on the GPU. So the real thing will be here in compute. So and in compute, we apply the stencil kernel for the computation. Sorry. And now we see some new construct which tells us that we will collapse the loops, the two loops for afterwards explicitly. But, okay, beside this, you recognize the same code inside the loops for the CPU and the GPU. The same goes for update. We collapse two parallel loops. And, sorry for the French, but this was a previous attempt here where I just defined a parallel region and I was hoping that the compiler would make the best out of it. So as you can see here, this is simply an array copy. There is an implicit loop in this expression. But in fact, the compiler couldn't make any performance out of this. That's a bit sad. And beside this, not much changed. Beside the end message. Okay, so now we'll have to compile this. And by default, I don't have the NVFORTRAN here. So I will set the proper variable for the NVIDIA toolset here. I source the file, and now I have this last NVFORTRAN version. Okay? Any question?
I don't want you to. You can.
I'm not using English.
Okay, so for the
Why do we put the compute in a subroutine?
OpenACC compilation, we go into the detail of the, yes?
So there is a question, why do we define the compute function as a subroutine when we have just two loops? Is there a particular reason for this, or just?
No. In the case of such a limited program, we could have everything in the same file.
Yeah, so just for clean code.
So yet another compiler, yet another set of options. -G is common. NVFORTRAN goes to -O for a very aggressive optimization. You tell the compiler that you want the accelerator, and that your accelerator will be the one with the native compute capability, CC native. So you could compile for some other machine by specifying the appropriate compute capabilities. You will be asking for information, all the warnings. This mdclcheck is in fact the implicit known like command, like flag. And as it is yet another Fortran compiler, we need yet another module for the HDF5 library. Okay, so before executing this, I had better move to the solution. Okay, so the file is here in the examples, this file here. And then we compile the ACC that we have just seen, and we link to the proper variables. So the optimization options are very verbose as well. It tells us that some loops are not fused and some are not vectorized. This occurs in the setup file subroutine, so maybe not the most interesting one. Write slice is doing I/O, so it's not operating on the GPU. Okay. Read slice, that's the same. The evolve routine, and in particular the compute routine, are the one of interest. So implicitly, he decided that the nx and ny variable will be copied and will have private value for each thread copied from the starting one. And here is the expected NVIDIA GPU code generation, and you get all the details that tells you, we just asked for ACC loop, and it told us, okay, I take gang vectors of 128 on top of our request of collapsing two loops. Is generating the data movement, copy out of V1, the implicit copy in of V0, U0, and also the copy out of U1. Okay. 14 seconds, it's rather good compared to, yes, we were at 16 seconds with G-Fortran. So, CPU with good vectorization compares to this GPU. So maybe we can improve things on the GPU side, but we are playing on the same level. And up to now, you see, it has been a couple of directives thrown upon almost normal Fortran code. So compared to what kind of effort would have been needed for Vulkan or OpenCL or others, it's rather nice. Okay. So maybe we should be looking for some other way to use the GPU. Or before moving to OpenMP, we would like to see what happens here. Oh, sorry, way to get it bigger. Not so much bigger. Okay. A bit bigger?
For me, it's okay.
So, as the common wisdom we get from the start of this school, we want to profile all our applications, and the same stays true for the GPU. Okay. So this is here that I should set environment variables. Okay. So the characters are big enough, but the details are tiny. So we see the span of the 14 or so seconds described. So we want to go into the detail. And we zoom out. And we see details at the level of the at the detail of the level of the millisecond. So okay. So we see that we have two kernels. Which is the compute on the update. So putting the two kernels in different routines help us understanding which is which. And in total, the GPU does not lose much time. You see this small gap between launching two kernels. And alternatively, it is going from the compute to the update and back. Okay. From this, do you get any idea to improve the code? Okay, we should keep in mind the main line of the talk is that computation is cheap. Memory is slow. And can we not get something better from this update? Because this is purely copying some memory in some other place. Whereas this is really computing something. So what I suggest is we get inside the update instead of the copy, the same computation but applied to U1 that will fill U0. And correspondingly for V. Okay, so now we have the same ACC parallel loop collapse. We have to define the Laplacian value. And we'll have to change something in evolve because we only need half as many steps now. So there should be a test because we expect that the number of steps is exactly an even number. So to compare to the other iteration are twice as fast, so we'll display things to compare previously. And during the update, we should write if twice the number of iteration is a multiple of intersafe count. Okay. So here it goes. Not bad. So as a reminder, we started with almost 14 seconds, and now it's only 8. Almost double speed up. Okay, so
but
yes?
The update is not even half the whole time. How do we get double speed up?
So
by cutting the time on the update in half, basically.
Okay, here we see, I have not yet changed the profiler. So we are on the profiling of the old one. We'll go into the detail. But in this profiling, you see that we spent on this kernel 257 microseconds. So this was the compute kernel. On the update kernel was 153. So some aspect of even the compute kernel is not purely computation. We move data.
Yeah.
So we could not expect completely a factor of exactly 2 because we have to spend some time moving data around. Okay, so how do we restart it? So same project, and now we restart. Okay. So now it's 50-50. We have the compute and the settings. Let us zoom somewhere here. Okay. This compute here for the update, which is a computation 266 microseconds, and here for the compute 266, 267 microseconds. So we have a very symmetric situation. So time for a break. So we'll be back at 16.